Gravitational lensing is a relativistic phenomenon caused by extremely massive objects such as black holes, warping the geometry of spacetime. As light travels through this curved spacetime, it bends and distorts, creating effects such as a warped imagery, Einstein rings, and photon rings. The aim of this project was to investigate whether industry approaches to gravitational lensing could be adapted into practical workflows for small-scale VFX productions, focusing on the balance between physical accuracy, render efficiency, and art-directability. To understand how these effects are recreated in visual effects, it's important to first understand the underlying physics. Gravitational lensing occurs because mass bends spacetime. Light follows geodesics, the straightest possible path through the curved space, causing the light to appear bent from the viewer's perspective. Around black holes, this creates several recognizable visual effects. The Einstein ring appears when light bends symmetrically around the black hole towards the observer. The photon sphere forms where light rays orbit the black hole, creating the glowing outer ring. Some black hole renders also include Doppler shifting, where colors change occur due to the movement and direction of light. These effects became the visual targets I aimed to recreate throughout the project. My research into industry workflows found very little published material outside the DNEG's paper on the DNGR renderer used for Interstellar. DNGR used ray marching and relativistic calculations to simulate light traveling through curved spacetime. Instead of tracing individual rays, it traced ray bundles to reduce flickering and create smooth IMAX quality imagery. While the results were extremely accurate, the workflow was computationally expensive. According to the paper, single frames could take between 30 minutes and several hours to render, even on DNEG's render farm. This highlighted a major issue for smaller productions. While physically accurate render creates impressive results, the workflow is often impractical for smaller teams with limited resources. The first workflow I tested was Matt Ebb's Houdini ray bending setup. This workflow traces rays from the camera and repeatedly bends them towards a singularity point based on distance. The final bent ray direction is then used to sample the background image and create the distortion effect. Although simplified compared to DNGR, the workflow still creates many important visual features of gravitational lensing, including Einstein ring distortion and accretion disk warping. However, during tests, I found the workflow highly technical, especially in its shader construction. While physically convincing, it was less accessible for the artistic perspective and required strong technical understanding to control effectively. The second workflow was my own custom STmap-based distortion tool created in Nuke. Instead of physically simulating ray bending, the workflow uses image distortion techniques to approximate the appearance of gravitational lensing directly in compositing. Unlike the Houdini workflow, this approach prioritizes art-directability and render efficiency over physical accuracy. While the results are not physically correct, the workflow successfully recreates many recognizable visual patterns associated with gravitational lensing, including mirrored distortion regions and photon ring effects. This is my custom STmap-based gravitational lensing workflow built in Nuke. The workflow functions by using an STmap that is distorted through multiple layered grid warp nodes. These distortions are then averaged together to create the final lensing effect, allowing control over both the internal and external distortion regions around the Einstein ring. The blend area between these distortions can then be intensified to simulate the magnification and concentration of light close to the black hole. The tool also includes a temporary 2D black hole element designed as a placeholder before the final CG black hole is created and rendered externally. Applied to footage, the workflow includes controls for position, rotation, and scale, allowing the effect to be art-directed live within the shot. The transform can also be linked to tracking data, either to integrate the effect into a moving scene, or to align the distortion with a tracked CG black hole render, removing the need for the temporary 2D element. The workflow then provides separate controls for both internal and external distortion strength, alongside controls for the blend region and light intensity, where the distortion compresses and magnifies imagery near the lens. Additional controls are included for the black hole itself, including adjustable blur and photon ray intensity for further artistic control. The workflow also contains a roto system allowing foreground objects to pass in front of the lensing effect without distortion. To improve render efficiency, the distortion calculations are processed internally in HD resolution before being reformatted back to the project's root format. Finally, the tool includes a checkerboard testing switch, allowing distortion patterns to be previewed and adjusted quickly during development. To test each workflow fairly, I used two forms of input imagery, a A simple checkerboard pattern was used as a baseline test, allowing for distortion patterns, Einstein ring formation, and overall image warping to be analysed clearly. I then tested both workflows using 4K footage to evaluate how effectively the effects integrated into more realistic cinematic imagery, whilst also comparing render efficiency and usability in a production-style scenario. In terms of render efficiency, both workflows were significantly faster than fully relativistic rendering. The Houdini workflow rendered HD EXR frames in approximately 24 seconds per frame, while the STmap workflow rendered a fraction of seconds per frame. This made the STmap workflow far more practical for rapid iteration and creative experimentation, especially for smaller productions with limited render resources. In terms of physical accuracy, the Houdini workflow produces more believable light behavior due to its simulated ray bending. However, the lensing lacked realistic spatial falloff and remained visible across the entire frame. The STmap workflow was less physically accurate because no real ray calculations were taking place. The final distortion depended heavily on artistic input and adjustment by the compositor. Despite this, the results remained cinematically convincing for many situations. To conclude, my research found that fully relativistic workflows such as DNGR are generally impractical for small-scale productions due to their computational and technical requirements. However, alternative approaches can successfully approximate gravitational lensing through selective simplification. The Houdini workflow provides a strong balance between physical realism and accessibility, while the STmap workflow offers a highly efficient and art-directable solution for small productions focused on cinematic believability rather than scientific accuracy. Overall, this project demonstrates that industry approaches to gravitational lensing can be adapted into practical workflows suitable for small-scale visual effects productions.